axis squared. If I have a complex situation like this, I just take each of the parts and I add them, put a plus sign in between them. That's the moment of inertia of the putty rod combination times omega. I'll just call it omega final. It is joined one object in the negative k hat direction, which we can easily rationalize the fact that the rod is going to be swinging clockwise, thumb points into the board. Through conservation of angular momentum, we have now a relationship over there that mass of putty times the distance of putty to axis times the initial speed of the putty equals 1/3 mass of rod, length of rod, squared plus mass of putty, distance at RP squared times omega final. Yes, please.
On the right side, why didn't you include the VR over RP? Yeah, that. Why?
Because ultimately the question is, what is the speed? How fast does the putty need to be going initially? So I wanted to work V into it. I could have waited, but I wanted to get a V in there because that's what we're trying to find.
Okay.
This is backtracking a lot, but where does the 1/3 come from? Like next to, you've got like 1/3 mass.
All right, so it depends on how far you want me to take it. The quick and dirty answer is that's the formula for a long thin rod rotating about its endpoint.
Okay, gotcha.
So
that's something that would be given to us?
Yes.
Okay. I thought at first it had something to do with like the length and like...
No, it's just the formula for long thin rod rotating about its endpoint.
Okay.
Okay, yeah. Then.
Why did you do that equation, the LP initial? The top right one?
This one right here?
Uh-huh.
I was slowly working into the fact that we could find an individual angular momentum by, yes, we have I omega, but also angular momentum can be found by R cross B, which I've erased. It was written somewhere around here. But I have two ways of finding angular momentum.
So did you use the angular momentum?
That this whole equation right here comes from angular momentum. This is the initial angular momentum of the rod, initial angular momentum of the putty, and then on the right-hand side, the angular momentum of the rod stuck to putty, or putty stuck to rod.
So in order to get the last equation, you have to do the equation on the top right one?
That,
Or
this right here is basically that. Not only basically, this expression right here and that expression right there are the same thing. Does that answer your question? Okay, Harrison?
Why is the initial angular velocity of the rod 0?
The rod's just sitting there.
Oh, just okay, okay. That's fine.
Yeah, when we shoot something at it, it sticks.
Okay, that's fine.
And how do you know that this is perfectly inelastic?
Because I said so. Yeah, it's part of the initial problem that it's perfectly inelastic.
If it was perfectly elastic, would the answer be different than this?
Yes.
Like both of them? Like everything is different? Elastic?
What would be different is if it were perfectly elastic, then the rod and the putty have different angular velocities after the collision. I don't know if the putty is going to keep going or the putty is going to bounce backwards, or probably in reality it would hit and then veer off in another direction. So combining the total moment of inertia with a single angular velocity would not work if we're perfectly elastic, or an imperfect equation, or collision. So I would still have, I'd have two unknowns after this, instead of just a single.
So in the second part of the equation, 1/3 mr L squared plus MP RP squared, I'm trying to figure out, like, since you're treating them as one object, I'm trying to figure out why you wouldn't have to use the 1/3 on the second part of the, like,
Because
you're adding the sum.
the 1/3 formula assumes you have a uniform rod.
Okay, so now that it's not uniform.
Yeah, then you have to
Okay.
either go through the calculus, or in this case, because it's just a point mass right here, I can just do the moment of inertia of one plus the other.
Okay, gotcha.
You said the 1/3 of the mass times L squared, that's the what of the rod?
That's the formula for the moment of inertia of a long thin rod rotated about in an end point.
Okay. Gotcha.
And because there was a reference to it earlier, if it rotated about the center, then that's 1/12 ml squared. And then on last Monday, we used the parallel axis theorem to derive the 1/3 ml squared from the 1/12, or vice versa. We derived one from the other. I know the videos from last Monday are up online. I can't remember if I actually posted the links. I was thinking I had. I don't know if you've looked.
No, I need to.
Yeah, it would fill in some of the gaps.
Okay.
All right, other questions at this point?
Yeah, so why did you include so when you were doing the angular speed for the putty and the rod, why did you only put the direction for the putty?
Oh. There we go. I should have. I mean, this ultimately is a zero vector because the rod's not moving to begin with, and so it doesn't have any impact. Formally, I should have added direction over here.
Okay, so anytime we find the angular speed, we should put the direction with it unless it's like zero?
If you're, the way you've worded it, I'm gonna base my answer based on your wording. If you're trying to find angular velocity, yes, there is a direction. You need to somehow acknowledge that direction. If you're trying to find angular speed, not necessarily. Now, because we're looking at an instantaneous value, how fast is, right after the collision, how fast is this thing going? Or right before the collision, how fast is this thing going? The angular velocity, instantaneous angular velocity, is just the angular speed in some direction.
Okay.
So that's why I could get away with, there's my direction piece, there's the magnitude, that's just the angular speed.
Okay.
All right, now, we have a formula now which will account for the collision. But how do we deal with the fact that it's going to go up 90 degrees? What physics principle is going to make this a whole lot easier? And I will say right now, if you want to do this from a Newton's second law approach, you are asking yourselves for a big headache. What is the simplest physics principle which will allow us to deal with an object, so that's putty and rod combined, moving up to here? If I want to figure out how fast it was going to start with.
It has something to do with the fact that it's a perpendicular angle, right?
The fact that it's perpendicular, I could have had to go farther and I still would have used the same principle. The fact that it's perpendicular will make some of the math a little bit easier.
Does it have to do with like splitting it up into a horizontal and vertical component?
Oh, that's making it more difficult than it needs to be. You could do it that way, but more difficult than it needs to be. after Newton's laws, we basically have only a handful of principles from chapters 7, 8, 9, and 10. We used one of them right here.
So we use conservation of momentum. Is that?
All right, you're thinking along the right lines, not conservation of momentum. That's actually not going to help us.
Conservation of potential energy, right? Or
Ooh.
because that has to do with height.
Work on the wording. You will close.
Just potential energy, then?
No.
Not necessarily conservation. Not necessarily conservation of, just like final versus initial.
Okay, we're bringing potential energy into it, but what's the principle?
Like kinetic energy changes into potential energy?
Okay. I was hoping someone would say conservation of energy, but
Oh.
yeah, ultimately, because we have kinetic energy being transferred into potential energy. What are the forces doing work on this thing? We have this rod and putty, or just, imagine there's putty on it. It doesn't change what I'm about to do here. As this thing moves up, what forces are, first off, what forces are acting on the rod?
Gravity.
What's the force?
No, weight.
Okay, and what's the other force acting on the rod?
A normal force keeping it up, I suppose.
Good. 10.
Okay, whatever the force is at the pivot point.
Keeping it there, yeah.
How much work is this force doing?
None.
Correct. This is doing absolutely no work because the torque is 0. Don't forget, we have our equations here. I know that what is the formula for work anyway?
Force times displacement.
And for rotational?
I times alpha.
That would be the total torque. I'm looking for work here. Rotational analog. What's the rotational analog of force?
Torque, right?
Times displacement? Angular displacement?
Angular displacement. Just transliterating still works. So the torque is 0. It does go through pi over 2 radians or 90 degrees. So delta theta is not 0, but torque is 0. So the force at the pivot point isn't doing any work. Which means we're only left with the only thing doing any work is the force due to gravity, which is, say, sorry?
Weight.
Okay, that's not what I was going for. Conservative or non-conservative?
Conservative.
Oh, it's
Thank you.
conservative, yeah.
Yeah, I don't know why I'm expecting you to read my mind today, but I was still expecting it. It's a conservative force, therefore energy is conserved. So, that depends upon where we want to make h is equal to 0. Where do you want to make h is equal to 0?
The pivot point.
Yeah, so
Okay.
just make it, yeah.
And so, let's see, I've rewritten, hopefully I didn't miswrite it over there. It's got MP, RP, VP is equal to U. All right, I feel like it's written correctly. final. 1F MV initial squared, let's try that one again. K initial plus U initial equals K final plus U final. Now it comes down to how we want to treat our two objects. We can treat them as separate objects, or we can treat them as a single object. Single object, we'll have to find the center of mass of the rod and pipe, which is doable. It's not an overly complicated process. Or we can treat them as separate objects. The amount of math is the same. Anyone with an opinion?
Separate?
Yeah, just keep it.
All right. I would have suggested that one. All right, so we have K rod initial plus K putty initial plus U rod initial plus U putty initial equals the same thing except final. K rod, KP, U rod, UV, final. What formula for kinetic energy should we use here for the rod?
Are you talking about like angular versus linear?
Yeah,
Angular, right?
Probably angular because it moves, yeah.
it's not all moving at the exact same speed as the thing goes, and so therefore, yeah, 1F I rod omega rod initial squared. Now the putty. It is a point particle. It would seem natural to use 1/2 mv squared, and we can do that, except for the fact that at some point we need to figure out what that is. Again, this is the post-collision, how fast that thing is going. The angular speed post-collision. So we could use the post-collision linear speed of the putty, and we're just basically introducing another variable that we don't have to. It's perfectly fine to do that, or we can just assume that we have a piece of putty that is traveling at some angular speed.
Would it be helpful to find it after the collision though? Because it's going to be different after the collision.
Yeah, this is after the collision.
Right. So does it really matter? Like, is it the same as before the collision?
No, it's not the same.
Okay, yeah. So we don't have to solve for it then?
We don't have to.
You said eventually we have to find that.
Oh.
Right?
No, I guess we actually, depends on where you want to, how many letters you want to do and when you want to plug numbers in. No, we don't actually have to. I am going to just suggest that we do 1/2 the I omega putty, omega putty. This is the rotational kinetic energy of the rod, rotational kinetic energy of the putty. Plus mass of rod, G, H rod initial, plus mass of putty, G, H putty initial. And then the exact same thing except final. So 1/2 I rod omega rod final squared. I putty omega putty final squared plus MGH MRTHR final plus MPGH P final. Now right now, it's potentially like just a bunch of alphabet, a bunch of letters just thrown onto the board. recognize that what we've always done is just initial energy equals final energy. That's the physics principle. We broke it down from energy into kinetic and potential. We broke it down one step further into, we have the kinetic and potential for the rod, kinetic and potential for the putty. At this point, now that it's all lined up here, we have our equation. What can we get rid of? What is zero?
H.
Which one? I got 4 H's here.
Yeah, that's a good point.
It's the final energy.
And why?
Because the height at horizontal is 0.
And why?
Because we said so.
All right, what else is equal to, can we get rid of anything else?
The initial kinetic energy for the rod.
All right, let's be careful about that. We got basically 3 situations. We have before the collision, just after the collision, and then into the problem. Our energy conservation starts after the collision. So our initial there is post-collision.
Okay.
Go ahead. Sorry, I was wondering if we were assuming the rod is stopping when it reaches that H equals 0 point.
Oh, it has to be. Otherwise, I didn't give you anywhere near enough information.
So our final speed, angular speed, would be 0 for the both of them.
And that's because omega final is equal to 0. So we have simplified that down. Hopefully this marker will show up. So I have 1/2, yes, times 1/3 mass of rod times length of rod squared times what I have labeled over there as omega F. Well, I would need to work on my subscripts here. Let's make this omega 2. Omega 2 squared plus 1/2 times the moment of inertia of that piece of putty, which is